Okay, I am talking about Enscripten, for those of you who haven't heard of it. And I will just start by saying, the reason I'm talking about this is, we talk about what you know, you can sort of pass on some of the knowledge. I've recently ported my game engine over to run on Enscripten. So I can now run my entire game in the web browser, and it looks exactly the same as it did when it wasn't running in the web browser, or as it does running on a tablet or anything like that. So for those of you who haven't heard of it, what is Enscripten? Rep this straight off the website, of course. It's basically taking LLVM. Can I actually just see, show of hands, who knows what LLVM is? Right. I really thought we were going to have a lot more than that.
My talk too.
Okay, yeah. So Manu's probably going to cover this a bit more in detail because. LLVM stands for Low-Level Virtual Machine. It's basically a compiler infrastructure almost. Everyone probably knows what GCC is, and which has been around since the 70s or whatever. LLVM is kind of now the next generation of compilers that is happening. It started out of a university project, and I believe it was Apple who put a lot of money into it and who really sort of championed it, pushed it forwards, and now it's kind of gone everywhere. These days, if you're, for instance, compiling some OpenCL stuff for the GPU, or a lot of GLSL compilers, that kind of thing, are now using it, and also lots of standard C compilers. You can use it to compile for Android. I believe the iPhone, it's definitely available, and I'm not sure, it may actually be the default in Xcode. You may not even know you're using LLVM, but you may be. Clang, yeah, I thought so. Does it?
Yes.
I wasn't sure if it was default yet. Is it default now? Yeah. Okay. So if you're using Xcode, you're already using LLVM. You just don't know it. And the difference between the old GCC stuff is it is meant to be far easier to extend and modify and do stuff with. It's a much more approachable code base. So people have started doing lots of fancy stuff with it. This being a perfect example. Somebody has basically written so you've got your front ends and your back ends to compile. Your front end being your language, and your back end being usually something like x86 or ARM or PowerPC, whatever you're outputting to. Some clever chappy thought, well, hang on, what if I write a JavaScript backend? So technically this means it's not a compiler, it's a transpiler, because you're technically converting from one language to another. But for the sake of argument, you can pretty much treat the browser and JavaScript as being like a virtual machine and say you're compiling for it. So generally speaking, you're usually taking C or C++, that's really what it's been built around, but technically, any language that could go into the LLVM compiler infrastructure could be put into it, and can be compiled and can get turned into JavaScript and run in the browser. And people have also, even interpreted languages, people have ported, I'll get into that, I've got that listed later. Lua, Ruby, Python, all these kind of things, a lot of these have been ported over as well. So you can pretty much, in a sense, take just about any language, compile it, and then run it in the browser. One of the big, once this came out, and it's been fairly successful, it's Mozilla guys largely running it. A lot of the momentum behind it now has actually largely come from the big game engine companies, because it is such a useful thing that they're kind of putting a lot of the push behind this. Okay, so on the web, the old plug-in based approach that everyone sort of knows about is there's been, you could write Java apps and run them in the browser, Flash Player, Silverlight. Silverlight's a fairly recent one, and everyone probably knows that there's been the Unity 3D player that people were using for quite a while. All of these things, of course, being plugins, and there's really been a big shift, as most people probably know in the web world, away from plugins. That's the whole idea of HTML5, if you've heard that term used, is it's meant to be putting those features directly in the browser and exposing them directly to the end user without needing to use a plugin to access the extra features. There's been other projects that have kind of gone along these lines before. I don't know if anyone's heard of these before. Adobe Crossbridge was a project that came out of, what was it called? It was called Alchemy originally. I can possibly put these slides on the website or something later if you guys want to be able to follow the links and go look these up. Basically, they built a project that, again, I think it also uses LLVM and compiles down to Flash. Apparently, if you took your C++ code and compiled it down to Flash using Adobe Crossbridge, it was about 10 times faster than if you actually wrote it in ActionScript. So again, even though that was your entire, because I don't believe ActionScript actually gets run directly, it kind of gets baked down to bytecode. So basically they just wrote a compiler that baked C down to bytecode, ran way faster. Whoever would have thought? And native client, again, native client originally was just using LLVM as the compiler infrastructure, but I believe there's now a thing called PNACL, they stick a P in front of the NACL, and that's portable native client, and that's kind of the future direction of it really. Again, show of hands, who's heard of native client? Okay, don't have to cover that one in such detail then. And I think there's a bit of a philosophical difference probably out there. Google have gone this very much approach of like it was pretty much native code and it just got sandboxed because everything in the Chrome browser was sandboxed in the end. And Mozilla sort of more went, well, hang on, why do we need to do LLVM and stuff? Why can't we just use JavaScript that's already out there and that already works in the browser? So how did we get to the point that this was possible? What was sort of the enabling things? JavaScript just-in-time compilers, as everyone probably knows, have been getting better and better for years upon end, to the point where, you know, they keep on claiming, you know, oh, it's 90% as fast as native or however many speeds, depending on what you run, of course. But the just-in-time compilers basically mean that if your JavaScript isn't in a loop, odds are once it runs a couple of hundred times, the just-in-time compiler is going to kick in and it's actually going to compile down to native code. You're going to be running native code. You aren't actually really running interpreted at all. And in some cases, it actually goes faster if you haven't hand optimized your code, simply because it's a bit like, for those who are really hardcore, if you've done profile guided optimizations, JavaScript always does profile guided optimizations. It does stuff based on how things are actually running on the actual data set you're giving it, and it can optimize for that exact case. As I mentioned before, HTML5 has been going on, and a lot of this is now providing lots of new APIs. Everyone knows about XHR, hopefully. XML HTTP requests, which is all AJAX type things, asynchronous requests for data going across the web. But there's also the orientation APIs now. So tablets in the browser, you can read the orientation and tilt of devices if you want to. You can read touch input directly. It doesn't have to emulate a mouse. There's now a gamepad API. You can plug an Xbox 360 controller in, and the web browser can use the Xbox 360 controller or any other gamepad. Now, also, most people are probably now aware of WebGL as well, which is basically a wrapper for the web around OpenGL ES. Specifically around ES, they use that as basically the min spec so that it can run on everything from mobile up to high end. So usually you're just sort of limited to that feature set. And when they started building this, they found, oh, hang on, we really need a way for people to be able to manipulate data and get it into GPU buffers, basically, so they can give us texture data and vertex data. So off the back of WebGL, typed arrays got invented, which, for those of you who haven't heard of it, is basically a way in JavaScript to basically say, create me an object that's basically a big list of bytes that's this size, and then give me a way to basically, for those who want to get really old school, peek and poke data right into that array. So effectively, when you sort of think about that, you go, well, hang on, I've just done a malloc, and I've just got a bunch of memory, and I can now do whatever I want with it. That's basically where this came from, because if JavaScript already has the operations in there, you know, that you can do with a CPU, add, subtract, multiply, all the usual operations, and then you can just make a big block of memory and you can address it by index. That's a Turing complete machine, basically. You can run software on that. So somebody wrote a compiler, made it so you could spit data out to run on this. And it's actually gone to the point now, ASM.js is now actually sort of a post-Enscripten thing. This has come out as kind of as a result of Enscripten. What ASM.js is, they now have a directive, they call it. If you put a little string at the top of your JavaScript file that I think says ASM.js, I can't remember exactly what the string is, it actually says, I'm not regular JavaScript. I'm a very limited subset of JavaScript that happens to look a lot like machine code. And the idea of this being, if you have compiled your C, C++ or whatever language code down to this JavaScript that looks a lot like assembly language, it'll run in any browser because it's just JavaScript. So anything that can run JavaScript can run it. You can put it anywhere, it'll run it. But for the newer browsers that sort of know about this, they spot that and they go, oh, hang on, I know this is basically assembly. So rather than waiting for it to run a few times before I kick in the just-in-time compiler, I'm just going to send it straight to the just-in-time compiler and turn this straight into assembly code right now. And not only that, when they actually do that compilation into machine code, they can also take a bunch of shortcuts because ASM.js is a limited subset. It doesn't let you do some of the other stuff that you can do with JavaScript with using closures and that kind of thing. It sort of just limits some of those extra features so that they can take a few shortcuts and make sure your code runs really fast. And this is all an effort, of course, towards making it so that pretty much the speed of your code that you've taken, your C++ code that ends up on this final machine, runs not as fast, but pretty damn close to if you just compiled it and ran it straight on the machine. And the difference is you're just sandboxed into a browser. So what kind of APIs can you use on this? Because, of course, that's what we're interested in if we want to port our games over to running in the web browser, right? An amazingly large array. So the standard C libraries, of course, that's a given. EGL, for those who haven't heard of it, which actually should really be sitting on this line down here along with SDL, GLUT, Glue, GLFW. I don't know if you guys all know these ones. These are basically your interface to, like, please give me OpenGL, give me something to render to. So that's usually setup stuff amazing. It does give you access to any of OpenGL, OpenGLES or OpenGLES2. However, as I mentioned, WebGL is really ES2. The other ones, effectively what they've done is they've kind of emulated them. I'll sort of cover that a bit more in a moment, just what's going on there with that. OpenAL is there for you, zlibs, libpng. And then basically pretty much anything that, if you can download the source code for it and run it through the compiler, then hey, you can use that too. And the thing is, this is now, I don't know if you guys look at that, that's pretty much the same set of APIs that are usually available if you compile to the NDK for Android. And most of that's also the same stuff that's available to you when you just do standard C on iPhone as well, I believe. And if you want it on Linux, you can do that. This is sort of becoming, in a sense, it's actually very similar to the same set of libraries you have access to for native client as well. And it's sort of becoming the standard POSIX set of libraries, really, that are all you actually need to run a game. So in a sense, you can build your game around these libraries for accessing, sound, graphics, file system, if you like, compression, and you've still got to map your input controllers based off the fact that your input libraries are wrapped around the web browser stuff. But pretty much you've got everything there you need to run a game engine. We don't really need anything more than that. Other libraries that have already been ported. I mentioned that you can just download, if you can download source code and compile it across. People, of course, have already grabbed a bunch of stuff. Bullets there, STB images there, OGG, Vorbis, Opus. A lot of that stuff you can possibly offload to the browser. And one of the things about it being a web browser is you can sort of drop into JavaScript if you like. It's a bit like writing like inline assembly. You can drop out and call out to straight JavaScript files to sort of do a bit of messing with the browser directly if you want. Free type, SQLite, and Lua, Python, and Ruby, and Perl. So people are now running other languages on top of this as well that are interpreted ones. Pretty much there's not really much you can't just run in a web browser as if it was like a virtual machine. 13? Yeah, okay, cool. I'm about on track. So as I mentioned, I've just ported my game engine across to this. So part of what I suppose I'm telling you, most of that you could have sort of got off the web in a sense if you looked far enough. This is the sort of stuff that I hit, and that if you're considering porting your stuff over to the browser, you're likely to hit. This is the stuff I hit anyway. The first one is if you're not already compiling against LLVM and Clang, you might hit issues with differences in compilers. Whenever you go between compilers, you can hit an issue where, this compiler treats things slightly different than that compiler. If you're already compiling through Xcode, you're using Clang, you're going to be right. That's not going to be an issue for you. You need a build environment to run it because these are basically, it's a bit like having GCC. Most people have hit this before. You get to a point you've got to decide what you're going to build it in. I'm not aware of there being any Visual Studio support. There might be. There is?
Very nice Visual Studio support.
Ah, there you go. Never mind, you just use Visual Studio. I use CMake for that anyway. You've got to get your environment anyway to set your project up so you can build it. Debugging is probably one of the biggest gotchas. Now, because usually you could, in theory, just be building stuff now these days, I think it's actually a pretty good option to almost just go, straight to the browser as a target that's considerable for this kind of thing and be writing in C and C++ instead of writing straight in JavaScript, because often your performance is better than straight JavaScript, which is the reason I'm a bit skeptical of efforts like Play Canvas that got mentioned at the start. I've sort of looked into that and it's all very straight JavaScript. But the thing is, of course, because it's an engine written straight in JavaScript, it's only ever going to run in the browser. Whereas if you write your code in C and C++ against this, you can run in the browser and you can also recompile and run at native speed on mobile if you want, which you can't do the other way around. But debugging is a bit of a hassle. If you're already running somewhere else, as usual, it's always best to debug the hell out of it on whatever your main operating system is, Linux, Mac, Windows or whatever, and then just try and deal with the differences when you get to the platform is always the best thing to do. Printf debugging goes a long way with it because you've got printf console output. You can breakpoint it, step through it, see what's going on, and it's actually amazingly good for that because it does actually use... I didn't know this until I did this stuff. Modern browsers, everyone's probably used the debuggers built into modern browsers. They actually support map files, if you can believe it. It will actually show you not the JavaScript it compiles down to, it will show you the actual original C++ source code, and you can step through it.
Are you serious?
Yeah. It blew me...
Line and file.
It blew me away when I first did it and went, oh my God, I'm not stepping through the compiled JavaScript that looks like assembly. I can just step through the code. Like I don't know exactly how they do it. The map file must include all the source compiled because...
I think it's just included in the file. It's called a source map.
Yeah, it's a source map, yep.
I think you just reference it from the top of the JavaScript file.
Mm-hmm. No, these ones stick it as like a directive down the very bottom. It's in like a comment, and the web browsers know about it, and they spot it, and they go, oh, yep, we want that. It must like I'm running it all through my stuff all through my own custom web server, and I know it doesn't have any access to all my original CPP files, and yet it's showing me my CPP source. So it must have all the CPPs and headers embedded in the map file as well. So the map file is fairly large. I did have to set it up once I realized the map file was there so that my web browser, my web server would serve the map file alongside the JavaScript compiled stuff. And as soon as I had that, I had full source debugging, which blew me away.
Source code from the web server, it just knows where it is in the local file system.
Surely it's just it's
well, you depends. Like again, I'm running my own custom web server, which is of course if you're doing something like Great Game is great because it can be like your multiplayer server as well. But if you're just running sort of Apache or something, I think you just toss both files in the same folder and it'll know where to find them and it'll pull it from the same location. You're done. Full source debugging. The only catch is, of course, you can't like in the converted source, you can't like hover over your variables in C++ and see the value of those variables. All the variables that you get for what values are just the JavaScript variables, which effectively end up being like looking through the registers window on a C++ debugger, if that makes sense. A lot of the naming kind of matches up, so you can figure out what's going on where. Helps to know JavaScript. You don't necessarily need to know JavaScript to use this approach, but it really does help, I think, especially if you sort of want to do any special funky hooks back into the browser to do your own stuff. Okay, I'm probably starting to run a bit short now, so I'll run through these a bit quicker, but these ones are almost a bit obvious. There's no file system. Well, there is, but it's a HTTP server. So now I mentioned I'd go back over the OpenGL stuff. It's OpenGL ES. You can compile anything that's straight OpenGL or ES1 and it kind of emulates it for you. A bit of where they've gone with this is they've really got lots of stuff, lots of coverage in there in terms of making stuff that's already there so you can just compile it and it will work. That's not necessarily the fastest route. There's lots of like compiler settings and that kind of stuff where you can basically either pick throw any old code at this thing and it will compile it and make it so it can run. Or you can go that, no, just give me a limited subset, but I want it to be the fast, efficient route. Now, if you're doing games, that's the one you're going to want. So they do actually have like an emulated file system where they'll download a bunch of files and stick them in memory, and you can access them with all the POSIX, and C-style file access functions and treat them like you had a file system there. But that's not necessarily the best approach. I actually preferred myself to actually hook it up and actually just talk straight to my web server and treat that as my file system because that's how my stuff runs anyway. And of course, so I think that's the better long-term approach is actually to treat this as its own platform, So there's no file system. You do have local storage. You don't have true networking, of course, but you do have, of course, pardon me, full access to XML HTTP requests, WebSockets, and WebRTC. If you haven't heard of WebRTC, that's basically UDP style, game style networking for the web browser. It's perfect for this kind of stuff going into the future, and means that along with everything else, we've really got everything we need to make games there. So it just, instead of opening up BSD sockets and writing to them directly, you just go through an interface, which I actually think is actually a good argument for using things like WebRTC as the protocols to your game engine. So when you're running on Android or something, I reckon just run WebRTC and WebSockets anyway. And then when you're in the browser, you just use them natively. And there's not really any reason not to, as far as I'm concerned. Obviously, you don't have true multi-threading. You've got web workers, so your engine needs to be able to switch back into a single-threaded mode. If you're relying on multi-threading, you can have some issues there. The really big one for me, where I hit a couple of bugs, was unaligned memory access. Usually, this is only a problem for things like on-the-wire network data, where you might be packing your data. Or in my case, the one I really hit was, it doesn't really show up until it crashes, is the real catch with unaligned memory access. Although I believe the most recent version is a bit better with that. The compiler will give you warnings and stuff. The header files for bitmaps, Microsoft's bitmap format, actually uses unaligned 32 bits inst and that kind of stuff, and it just crashed on me and took me ages to figure out why, and it was because it was an unaligned memory access. So the stuff I described about it gives you a big block of memory and says, here, go access it. Because of the way it does it all in sort of discrete chunks, you can't do unaligned memory access. So if you want to load a 32-bit number that's 16 bits out, you need just pull up the bytes or something and repack it.
How does the browser handle the crash?
Sorry?
How does the browser handle the crash?
Throws an exception. So you get a call stack and everything. Like it's actually, so you get a call stack, you know, where it crashed, and you just kind of stare at it for a moment and go, why the hell did that crash? Because everything, you know, the code looks fine. The way, like, because of the way it does memory accesses, it's kind of like a massive union, if that makes sense. So you've got a big block of memory, and imagine you had a union array over the whole thing, where you can access it as bytes, in which case your pointer would just be directly, you know, my pointer is the same as just an index into that array. And if it's a 16-bit value, it's kind of, you take your pointer and you shift it right by 1. Is that the door or something? And if it's a 32-bit number, you do a shift right by 2, if that makes sense, and that gives you your array index to the array of 32-bit values. Now the catch is, if you're doing unaligned memory access, you've got, and then when you do that shift right 2 to get your array index into the array of 32-bit values, you just dropped your lowest bit that was a 1 that was giving you your unaligned access, and instead you end up 2 bytes out, if that makes sense. So dodgy access, you pull in some weird value. No, I was looking at a bitmap info header. It ends up being offset by 2. You get some, you know, you get the magic value at the start of your number, and you know, your little endian where your big endian should be, and it just goes to hell and throws in a cert. So anyway, that's just one to watch out for. Having unaligned memory access is kind of...
Fix the readjustment of bitmaps?
Well, because of course it's just a couple of bytes you've got to worry about, I just pull it in byte-wise, and then just do a couple of shifts to pack it together into an integer on the CPU, if that makes sense.
Every time you load it in C, or like do you just...
Yeah, well, that's to be able to do it in C, yeah. That said, that's the way I was doing it because I hadn't done a get latest on LLVM in a month or two. The very most recent one, where I just got it this week, they've now added support where you can actually use a compiler directive through LLVM that basically says this pointer or this variable I'm accessing is unaligned, and then the compiler will just do it for you. So that's it. This is one of the things I really hit with this. Lots of things where I ended up writing workarounds for things or writing my own implementations. This stuff is moving so fast at the moment. I do a get latest and somebody's, you know, that they've whacked in a new implementation that completely covers the problem you just worked around. So
Commits to Enscripten a day.
Yeah, yeah. And which comes to my last point, which is bugs in the API was the other problem I hit because it's developing so fast. There is so much to this that every now and then you will actually find bugs. But the thing is, they often get fixed before you can even log your bug, kind of thing. How am I doing for time? Right, okay. So there's the philosophical questions behind this. Like, is this the right approach? Is the NACL approach better? Of like, hang on, we're compiling to JavaScript, and basically just trying to get assembly at the end from C. Why don't I just go straight there? Why are we going this roundabout route? Isn't that a bit odd? Mozilla's point is that, well, JavaScript's already there everywhere, and you can run it everywhere, and everyone can read the source code. But like,
the world's most popular browser, and Mozilla are just being dicks.
Yeah, and the thing is, and you look at this and you go, well, 10 years down the time, are we going to be in this weird thing where everyone's just compiling their C to JavaScript, so it's become this weird new. And my answer to all that is, who cares? We're game developers, and we've got C code, and it can make something that runs on the platforms where we want to be. Like, I can't be. If somebody comes along and if NACL wins, or this wins, or mobile wins, or whatever else, if you write against these kind of C is the language that runs everywhere, and now it runs even more places. Just if you write your stuff against this stuff, you can run everywhere, and let the world figure out which one's going to win. Just why not be able to support it, though? It's another place for people to play your games. Why not? Why would I want to do this? Because the web browser is everywhere. If people, and increasingly there's stuff like Chrome OS laptops, which are getting surprisingly prolific. A lot of corporations and schools are now giving them out to students or people because they want them locked down. They don't want people installing stuff. But people still want to play games on those things. That's a great market for this kind of thing. Why wouldn't you? This stuff, and WebGL's apparently on. I saw in the news at the start on iOS now even. It's a really easy entry for people. There's no download and install. You go to the web page. You only need to pull down as much data as you're necessarily showing at one time. So it's a really soft entry for somebody into your game, if that makes sense. It's just go to a web page and hey presto, somebody can follow a link and they've got your game.